Whether my screen is visible to you?
Yes, sir. Yes. Yes.
Okay, fine. So, good evening, students. So, in this session, we are going to discuss about Rayleigh flow, span of flow, and wind tunnels. So, in wind tunnels, high-speed wind tunnels and low-speed wind tunnels. So, first of all, we will discuss about the Rayleigh flow. So, Rayleigh flow is also called as a constant area duct flow, where there is no friction, only there is a heat transfer in this. So we call it as duct flow with heat transfer and there is no friction. Then that flow is called Rayleigh flow. So in what the assumptions for Rayleigh flow are, it should be a steady one-dimensional flow because the flow is in one direction only, and there will be no heat transfer and should be a constant area duct, and the gas is a perfect gas and there is no work transfer and there is no friction also. So now before in our last class and all we discussed about the flow over nozzles, flow over variable area duct, quasi one dimensional flow. In quasi one dimensional flow, the area of the duct varies with respect to x, with respect to the length of the with respect to the length. But here, no matter what the length, the area remains constant. That's why it is called constant area duct. And we are going to discuss about the flows in the constant area duct when there is no friction but there is a heat transfer between the duct and the flow, that is addition of heat and rejection of heat. So that type of flows is called Rayleigh flow. So here we can see a control volume. So this is the control volume, the boundary of the control volume. Here is the, it is in dotted lines. The Q is the heat transferred from outside to in the flow, and the rejection also. Here there is a two type of heat transfer is happening. One is the heat addition and another one is heat rejection. We will see both the types in this flow, and here we can see the flow parameters like pressure in the inlet, we call it as P1, temperature T1, density ρ1, and velocity v1. In the same way, and at the exit we can exit of the control volume, this is the exit of the control volume, and we call that parameters as pressure P2, temperature T2, density ρ2, and velocity v2. So here it is a constant area duct. We can call it as, we know the mass flow rate m equal to rho a v. So from that m by, we know m by a equal to rho into v. So from that v equal to, we can call this m by a as g. So v equal to g by rho. So here from this continuity equation, mass equation, we can we know rho1 v1, rho1 a1 v1 equal to rho2 a2 v2. Area is constant, therefore a1 is equal to a2. So from this rho1 v1 equal to rho2 e2. Same way in momentum equation, p1 plus rho1 v1 square equal to p2 plus rho2 v2 square. We know from this momentum equation we can write like this also. Before substituting the terms of from inlet and outlet, we can write like this: p plus rho v square equal to constant. So p plus rho into g square. Substitute the value of v square, v here. So g square divided by rho square equal to constant. So here from this row cancel, so the equation reduces to P plus G square by rho equal to constant. So we know 1 by rho equal to, we can write like this, V. So P plus G square into V equal to constant. This is constant. So this equation is the equation for Rayleigh line or Rayleigh curve. So we have a Rayleigh curve here which determines the flow for when it is plotted for temperature and entropy, or enthalpy and entropy. For that we have a curve plotted for this, and the curve is called the Rayleigh curve. This equation represents the Rayleigh line or Rayleigh curve for that flow, for this constant area duct flow without friction. So here are the for energy equation, we know there is a heat addition, therefore Q equal to Cp into T2 minus T1 plus V square minus V1 square divided by 2. This equation H1 square plus H plus so Q equal to Cp into T2 minus T1 plus V2 square minus V1 square divided by 2. We know Cp into T equal to H. So H01, H02 minus H01 equal to Cp into, we know that Q equal to Cp T0, Cp into T0. So therefore from this equation we can write like this, Q equal to H02 minus H01 equal to Cp into T02 minus T01. Same way for entropy change also we can write like this, the S2 minus S1 minus Cp ln T2 by T1 minus R ln P2 minus P2 by P1. And also this is the entropy change equation, this is the energy equation, and we have seen the momentum equation and the mass equation for this. And we know from this P equal to rho RT formula, there is equation of state formula. From that P by rho T equal to, it will become constant, so P1 by rho 1 T1 equal to P2 by rho 2 T2. So these are the parameters and the equation for this Rayleigh flow. So here we can see the Rayleigh line. So in actually this Rayleigh flow and Rayleigh Fano flow, there will be some questions regarding the theory questions only. That means objective type questions only, not solving type questions, because for solving it will the problems are very big, so they won't ask such type of problems here. And we need in order to solve the sums we need fully gas tables for that, so they won't ask questions regarding that or problems regarding this Rayleigh flow and Fano flow. But what they will ask means they will ask the flow parameters how it is changing because of this Rayleigh curve when we are applying, or when we are adding heat to the duct, or when we are removing heat from the duct. When we are by this two process, what is happening, they will ask the what are the parameters will change, that is static temperature, whether it will change, or the Mach number, whether it will change when we are adding heat to the flow, or heat to the flow in a constant area duct. That we will see here, that the questions will be in that format only. So here we can see the curve in the right hand side, top right hand side. Here MAB equal to 1 by root K. So here this K, it denotes the gamma. So I took this from one book. So in that they have denoted the term gamma as ratio of specific heat as K. That's why here it is a K. But in real time we will, it is this K is gamma only. Gamma equal to 1.4. There is a ratio of specific heat. So here this in throughout this Rayleigh curve and Fano curve, this K represents only gamma only. So just note that, because you don't know whether don't think it is a new term, it is just gamma only. So here the curve is plotted for temperature and entropy term, yes, or we can say it as a enthalpy and entropy term? Yes, because we are supplying heat to the duct, or else we are removing heat from. That is means heating and cooling is done in for uh, heating and cooling is done. That means we are removing heat from the duct, and or also we are adding heat to the duct. Okay, that means a flow in the duct. There only we are adding heat. So here we can see this points like A, B, and a curve here. In the top side also we are heating the flow of gas, and here also in the bottom side also we are heating the flow of gas. But beyond this B direction, when we are applying heat to the flow, what will happen means the Mach number, it will keep on increasing. The Mach number will increase when we are applying heat to the flow. So here it is subsonic flow, and here it is supersonic flow, that I need to mention first. And so when we are applying heat to this duct in a subsonic flow, the Mach number will increase. The Mach number will increase, and it will increase up to m equal to 1. That is, it can increase only up to sonic condition. But in a supersonic flow, so if a supersonic flow is flowing in a duct, or supersonic gases or air is flowing in a duct, in a constant area duct, when we are heating the gas, what will happen? The Mach number, it keeps on reducing. The Mach number decreases when we are heating the duct. So if you are heating the duct, the Mach number, it keeps on reduces, and it reduces up to m equal to unity. That means m equal to 1. Just note down these two things, that are only important for this. If you are for a subsonic flow, if the flow is subsonic, and see from here to here it is subsonic, the line is subsonic, the Rayleigh curve will be subsonic, and the bottom portion from A to the end of the curve, it will be supersonic. Okay, so this is the maximum entropy. These conditions are the maximum. A and B conditions are the maximum. A condition is the A point is the maximum entropy region, and also the B is the maximum temperature region for this curve. So the curve above is subsonic, and the curve below will be supersonic, and this condition is called the choked condition, that we will see in the next slide. So this is the choked condition. So when we are heating the gas or air in a subsonic flow, Mach number increases. When we are heating the flow of air in a supersonic flow, the Mach number decreases. Here also the Mach number increases up to unity only, that means sonic condition only. Here the Mach number will decrease up to sonic condition only. Okay, have you noted down this point, guys?
Yes, sir.
Yes, sir.
Okay, fine. So here you can see this entropy, it keeps on increasing with heat gain, because you can see here the heat is we are applying heat, the entropies keep on increasing. If you are removing the heat, means the entropy keeps on reducing. Thus, because of this entropy, there will be a heat transfer to the fluid. So here the point is here only, that is heating increases the Mach number for subsonic flow, but decreases it for supersonic flow. Okay, so another one thing here, when Mach number increases, velocity increases, and also the static pressure, it decreases. But in supersonic flow, when Mach number decreases, automatically velocity decreases and the pressure increases. Same thing for density and velocity also, they are inversely proportional, that you can apply here. And for entropy, the entropy change corresponding to a specified temperature change is large in, the entropy change will be larger in supersonic flows. Okay, so here we can see the conditions, or the parameters, how they are changing for subsonic and supersonic flow, and heating and cooling. So here cooling itself, so for heating the subsonic flow, Mach number increases, but while cooling the Mach number decreases. The opposite will happen for cooling. The condition opposite will be happening for cooling. That means Mach number decreases in subsonic flow, and in supersonic flow the Mach number, it keeps on increasing when cooling the air. Okay, so in a constant area duct, if you are cooling the gas, uh, for a supersonic flow Mach number increases, but for subsonic flow Mach number decreases. Okay, the opposite will be happen for when we are heating the flow of air in a constant area duct without friction. Okay, so remember this Rayleigh flow means there will be no friction in the flow, but there will be a heat transfer in the flow. But for fan of flow the opposite is. So one more condition for this Rayleigh line, that also they will ask. The thing is about the static temperature. The static temperature in the will increase if M infinity is less than 1 by root of gamma. If the static temperature will increase if M infinity is less than 1 by root of gamma. This 1 by root of gamma is represented as 1 by root of k here. Okay, then static temperature decreases. The static temperature decreases if M infinity is greater than 1 by root of gamma. So the condition is the static temperature in a Rayleigh flow increases when M infinity is less than 1 by root of gamma. The static temperature decreases if M infinity is greater than 1 by root of gamma. Okay, so here we can see the parameters which is increasing and decreasing for both subsonic and supersonic flow when we are applying heat or reducing heat from the flow. So velocity, the velocity term, it increases in subsonic flow for during heating. First we can say about heating. Velocity increases and velocity decreases in supersonic flow. Mach number, if velocity increases, Mach number will also increase. Same here, if velocity decreases, Mach number will decrease. And also the stagnation temperature increases for both subsonic and supersonic flow, since there is a stagnation temperature, it will increase. That I will tell you why it is increasing. And temperature, the static temperature, I told the condition that it increases for M less than 1 by root of gamma, and also decreases for M greater than 1 by root of gamma. And the opposite will have same. And density term, density is decreasing because velocity increases means density decreases. The opposite is happened for supersonic flow. And the stagnation pressure, it decreases. Here also the stagnation pressure, it is decreasing. The static pressure is decreased when because here the velocity is increased in subsonic flow. Here the velocity is decreased in subsonic flow, therefore the static pressure increased here. The entropy term, it is increasing for subsonic and supersonic flow, that we can see here. The entropy is increasing here while heating. Then for cooling, you can see here, upon cooling the entropy term, it decreases because entropy is decreasing upon cooling. So here they are representing as entropy decreases. Same velocity, remaining things, the velocity for during cooling in subsonic flow, it decreases. Mach number decreases. Same way stagnation temperature decreases. Then temperature, it decreases for Mach number less than this condition. This both condition, please remember, because they will ask this type of questions only. Density also, it increases because the velocity is decreasing. Stagnation pressure, it increases. Pressure, because density is increasing means automatically pressure is increasing, and the entropy, it decreases upon cooling. Okay. So this is the some formulas for finding the Mach number, because yeah, for your in order to find solve some problems in Rayleigh flow and all, they will ask us to find the pressure ratios, and also the exit Mach number. They will ask the condition for the exit condition. They will give the conditions for initial condition they will give, and they ask us to find the final conditions, because they will give these values, and they will give this m1 value also, and they ask us to find the final value for that for pressure, temperature, for these flow parameters they will ask us to find, and also the exit Mach number. But for your gate and all, they won't ask this type of questions and all, because it takes much time, and we need gas tables only for solving this, otherwise we can't solve. So these are the formulas. Please note these formulas also. Please intimate me when you finish noting down. In our end session of this class, I will show you how to pick values from gas tables and solve the sums. Okay, so you may know how we are picking the values and all.
Sir,
Yes.
sir, why stagnation temperature increases for both subsonic and supersonic, and normal temperature, static temperature decreases for supersonic?
This, for Rayleigh flow, you are asking here.
Yes, sir. Yes, sir. Stagnation temperature increases in both cases, but static will decrease in supersonic flow. Why it is, sir?
Yes, for heating, uh, the temperature is depend upon this enthalpy.
Yes, sir.
We know that H naught equals to Cp into T naught. When
Yes,
temperature
sir.
increases, automatically the total temperature is also this total temperature will increase. But for cooling, the temperature is decreasing. That's why the total temperature it decreases. Okay.
Sir, total temperature increases for both supersonic and subsonic.
Yes. In both cases, we are heating the flow. If we are heating the flow means automatically temperature is increasing. That's why the total temperature increases. Okay.
So then why static temperature decreases in supersonic?
Static temperature depends upon that gamma value now. That's why,
अच्छा, ठीक
because
है
of the
sir. Okay, sir.
conditions. That's why they have given the conditions like this. It increases for a Mach number less than 1 by gamma of square root of gamma. We can apply that. We will know.
Yes, sir. Yes.
So you finish this noting this formula.
Yes, sir.
Okay, fine. So then we have the choked condition is in Rayleigh flow. That means when the Mach number will reach unity, the condition will become choked. That means it won't allow the super subsonic flows. If the subsonic flow it reaches unity, means it can't go beyond supersonic flow. And also in uh, if a supersonic flow it reaches unity, means it go beyond subsonic flow. That's happens when a Rayleigh flow is choked. When this condition occurs means if Mach number when it reaches unity, this choking will occur. in the here we have the formula for this maximum heat transfer for this choking flow, that is Q max equal to H naught star minus H naught 1 equal to same. See there we seen about the T naught 2, but here the T naught 2 is choked condition, therefore we mention the term as T naught star minus T naught 1. So the limit is T naught by T naught star equal to 1 minus 1 by K square, that means gamma square. So for gamma square it yields, we know gamma equal to 1.4, therefore gamma equal T by T naught by T naught star equal to 0.49, and the for the critical, if here we have a condition, note this condition also, if the critical stagnation temperature is 1000 Kelvin, if the critical stagnation temperature is 1000 Kelvin, the air cannot be cooled below 490 Kelvin. So the critical condition means, so this is we can see here this critical conditions. So these are the critical conditions. It cannot go beyond this critical conditions. So if the maximum temperature is 1000 Kelvin means, and it cannot go beyond this limit, that 490 Kelvin, it won't it cannot be cooled, the temperature cannot be cooled below 490 Kelvin. That's conditions here. And I told that for a supersonic flow, if you are cooling the gases means it will increases now. So for what the, so here it is here, when a supersonic flow cannot be sustained, the flow undergoes a normal shock wave and becomes subsonic. Okay, a supersonic flow cannot be sustained, it cannot be sustained there if the flow undergoes a normal shock wave, the flow undergoes a normal shock wave and becomes subsonic. Okay, so this is about Rayleigh flow. So in a Rayleigh flow you should remember certain conditions. The condition one is about the static temperature, and other thing it is it should be under choked condition, the choked flow condition, and also about the constant area duct, and also about there is no friction and only heat transfer, and temperatures are that depends upon the heating and cooling process, and the flow parameters. These things you need to remember, because they will ask questions whether the static temperature will increase or decrease, or whether the velocity increases or decreases, or during heating the Mach number whether is it increasing or it is in a decreasing manner, that we need to remember. Okay, so next thing is the fan of flow. So fan of flow, it is also the flow in a constant area duct, and it is also a one-dimensional flow, but only thing is there is no heat transfer. That's why it is called adiabatic ducts, because in adiabatic flow there won't be any heat transfer, and only thing is there is friction. This how we know the term, like if the length of the duct is more in a flow, there will be a friction in the flow. So here the final thing they ask us to find is the length of the duct. So if they are asking us to find the length of the duct, we can easily identify that it is a fan of flow. In some problems there will be some confusions, like they won't give the term like friction and all. They ask us to find the length of the duct. So if they are asking us to find the length of the duct like that, means we need to think that it is a fan of flow. Here also, so these are the, so same type of graph is there for fan of flow also, but here if the length is increased, some changes will be occurred for Mach number and other flow parameters, and also for supersonic flow. In the same way, if the length is decreased, something will be happened for subsonic flow for Mach number and other parameters that we will see here. Here there is no heat addition, therefore the temperature terms and the stagnation or total temperature term, it remains constant. So the assumptions are a steady flow should be there, and consider it is a steady one-dimensional adiabatic flow with constant specific heats. through a constant area duct. So we should have a constant area duct and a one-dimensional flow and then a steady flow and also adiabatic flow with the friction effects, but there is no heat transfer. That is adiabatic flow. Okay. So here same way, here also we can consider the continuity equation for fan of flow. That is rho 1 v1 equal to rho 2 v2. That is equal to, that means rho v equal to constant. From that for initial and final condition they are giving rho 1 v1 equal to rho 2 v2. The same way the momentum equation P1A minus P2A minus F friction, because there is a friction, but in Rayleigh flow we have the term like Q, that is equal to m dot v square v2 minus m dot v1. That means P1 minus P2 equal minus F friction by A, that is equal to rho 2 v2, that is a m dot we are giving considering rho 2 v2 into v2 minus rho 1 v1 into v1. So the equation becomes, and P1 plus rho 1 v1 square equal to P2 plus rho 2 v2 square plus F friction divided by A. And for the entropy change we are giving this equation S2 minus S1 equal to Cp ln. So these equations, we don't need these equations because this is for deriving. Actually the main thing is it is a big derivation. There we need to derive equations for T2 by T1 and the impulse function, and also for frictional friction coefficient, and also for the to find the length of the duct we need to derive some equations. So in order to derive this equation we are using this basic equations like entropy change, energy equation, and for ideal, because it is a perfect gas, then del H is equal to Cp into del T. That means Cp into T naught. Therefore T1 plus V1 square by 2 Cp equal to T2 plus V2 square by 2 Cp, and we know there is no heat addition, therefore T01 is equal to T02. And here this why they are giving A1 equal to A2 means it is a constant area duct. Therefore here by substituting this T0 here, it is T0 equal to T plus V square by 2 Cp. So from this equation also you can, you may know in previous equation also we can see here if velocity increases what is happening, velocity decreases what is happening. For Rayleigh law also we are having such equations. From that we can easily say, and the equation of state also P1 by rho 1 T1 equal to P2 by rho 2 T2. So here this is the fan of flow curve. This fan of flow curve is so for fan of flow also we have this yeah, we know this m dot m equal to rho a into v. We know this m by a equal to, this is not m dot, that is mass flow rate, m dot a equal to rho into v. We can consider this rho vs. sorry to say this m dot as m dot divided by a as g, so that is equal to rho into v. So from that v equal to g divided by rho. So this is the equation for Fano curve. This Fano curve depends upon this equation. So here as I told, there is a friction in the flow, and we need to find the length of the duct. So because if you are increasing the length, there will be the Mach number increases in subsonic flow, and if you are decreasing the duct, the Mach number decreases for supersonic flow. So for subsonic flow, if you are increasing the length of the duct, if the length of the duct is increased, Mach number is increased, and if the length of the duct is decreased, if it is a decreased Mach number, it is also decreased. So and here also the condition remains same for choking point. That means the Mach number, it will increases up to unity only, and here also the Mach number it decreases up to unity only if you are increasing the length. If you are increasing the length, the Mach number decreases for supersonic flow. That means m decreases, here the m increases. Okay, by increasing, same thing for we are increasing the length. So here also the for a unity condition that we will call it as a choking flow. This is a choked flow when the Mach number m is equal to 1. When m becomes critical value, or there is a m equal to sonic condition, the condition will be choked flow. Then the flow is called choked fan flow, and the length of the duct will be critical length. Then we will call it as L star. So here, as I told earlier, that m Mach number increases. Here the properties of the when there is a friction and there is an effect of friction, what has happened for subsonic flow, and when there is an effect of friction for supersonic flow, the change in property is mentioned. That is a velocity, it is increased for subsonic flow. Mach number, if a velocity increases, Mach number increases, and the stagnation temperature, it is constant. Temperature decreases, and density is also decreased. The stagnation pressure, it decreases, and pressure, it is decreasing because the velocity is increasing, and the entropy, it keeps on increasing. That we saw in across the shocks also, we saw that there's a entropy is increasing. In the same way, the velocity decreases, Mach number decreases in supersonic flow when there is a friction, stagnation temperature. You can note down this properties for this. Let's just note down these properties for fan flow. When there is a friction, what is happening for subsonic flow, and also for supersonic flow, what is happening when there is friction. Just note down these things, this table. Just note down this table.
Sir, hello, sir.
Yes.
Sir, how do we like remember this property? Because Rayleigh and fan flow, it's like bit confusing, sir. Both are like increasing, decreasing.
Yes.
So, is there any way to remember?
See, the simple thing is there's no way like that, but we can remember like from this curve, because both the curves are same for this Rayleigh and fan flow, and there will be a choked point. It's the maximum here. We have in Rayleigh flow, we have this maximum temperature here. We are plotting it for temperature and entropy. That means enthalpy and entropy. Consider this enthalpy. If temperature is increasing, enthalpy increases. That also you should remember, because it is for TS and HS. If it is a TS diagram, it is a HS diagram also. So here also you can see here in both side, top side is subsonic, and the bottom side is supersonic.
Supersonic.
Yes, both bottom side is supersonic. Okay. And here also in both side, while here we are heating in Rayleigh. This is Rayleigh flow, so I am writing as R. Yeah, this is fan curve, so I am writing it as F. Okay. In both sides, over the top side, that is for subsonic flow. If in Rayleigh flow we are heating, here we are increasing the length. Okay, so you can see here, if the length is increased here, velocity increases. So here also, when we are heating, velocity increases, or we can say it is Mach number. Mach number, while heating, it increases. Here also increase when we are when there is a friction, or when we are increasing the length, Mach number increases. Okay. The opposite is happening for if you are heating the supersonic flow, Mach number decreases. Mach number decreases. Here also Mach number decreases if you are increasing the length. So we can say just first of all, if they are asking some questions about this Rayleigh flow, means just draw this diagram, so that by drawing this we can easily say that some properties from this, because if pressure is increasing here, we know that if Mach number increases, what will happen? Temperature decreases, pressure decreases, density decreases. Okay, these things we can say from here. If same way, for if the Mach number is decreasing, these things will increase. So it will is common for both, for both. Then we know this is a in a fan of flow, it is a adiabatic flow. So therefore T01 is equal to T02. That means T0 stagnation temperature, it remains constant, and the stagnation pressure, here the stagnation pressure is decreasing. So for here the both the stagnation pressure is decreasing, and we know there's a entropy is changing, because the entropy is increasing only. Here we are increasing the length, so the entropy is also not because of that increasing length and all, but here the entropy is increasing only. So likewise you just remember, so one or two things only, it is a little bit complex for you to remember, but other things you can easily remember from this graph itself. Okay.
Okay, sir. Okay, sir. Thank you.
Okay, fine. So here you can see the formulas for fan of flow. Just note down this formulas. The star represents the choking condition or the critical values at the duct. Okay, if there is a critical the L star means it represents the critical length. Other star and all, it represents the point where, or the place where the Mach number equal to 1. That means the choking condition is occurred, or sonic condition is occurred in the flow. So from this formula only we will determine the length of the duct. By using this formula only we will determine the length of the duct, and these things and all we will collect the pick the values from most of the things we will pick the values from gas tables only. We can see the gas tables for both isentropic flow, or for all flows we will be seeing the gas tables. That I will show you the gas tables at the end of the session. We can discuss about the gas tables, from where we need to pick the values and all, that we will see. Okay, so just note down these values, these formulas.
Sir, DH is diameter, na?
Yes, diameter of the duct.
Okay, sir.
And in your end section I will show you the theta beta m curve, and also how the shock is formed in a supersonic flow. That means in a convergent divergent duct, how a supersonic flow is formed, and how shocks are occurred inside the duct of the convergent divergent duct, and what is the pressure ratios. Last class itself we have seen, but we didn't see the pressure ratios in one single image, that I will show today.
Sir,
Yes.
why this relay flow and fan flow is concentrating more on ducts? Why not other?
See, it is an one-dimensional flow. So in a one-dimensional flow itself, we can say it is a it will be in a duct. can't do it for varying rectangle. For a quasi-dimensional, quasi one-dimensional flow and all, we can't mention this type of flows. That's why. So in a long tube, if there is a flow, if the flow is supersonic or subsonic, we can consider this type of flows. Okay.
Okay, sir.
So have you finished?
Yes, sir. Mine is done, sir.
Okay. So next topic is about the wind tunnels. So you all know about wind tunnels. So wind tunnels are, it is a device which is used to test a model by the flow of air into the test section. Okay. So we know from Wright brothers, they have also tested this models in wind tunnels. From that time itself, wind tunnel is popular. And because first of all, why they have designed this wind tunnel means, if we can't design a whole aircraft, or we can't manufacture a whole aircraft and fly, uh, after flying we can't get the values, or we don't know what is the parameter when we are flying at some height, and what is the impact of air when we are flying at some altitude, but that we don't know. If we are not considering the factors, we can't fly in a steady manner and all. That's why the aerodynamic effect is, we should consider the aerodynamic effects. That's why wind tunnels are made. And because of the wind tunnels only, the aerodynamic properties are determined in those days. Now there are no so many softwares for determining the aerodynamic efficiencies, aerodynamic properties and all, but still there's a lot of difference for software and also for real-time values. Because the real-time values, it changes when we are comparing it with the softwares and all. And also, but now they are considering another one projects, like they are working on projects like artificial data acquisition like this. That means if you are giving some aerofoil, and we are telling that yeah, it is flying at some or it is, we need to estimate the flow parameters or aerodynamic parameter for some velocities, means it can easily, it will run some simulations, and it will easily give the values for this. Automatically the values are predicted, but it is based upon artificial intelligence. Some research work is going on, recent research works are going on that for that. But still we need wind tunnel for our ease, and also for our perfections and all. So there are two types of wind tunnel in a general point of view, that is a low speed wind tunnel and a high speed wind tunnel. But in most of the colleges and most of the places, we have this low speed internals, that I think you may saw this low speed internals and all. So the low speed internals itself, it is classified into open type and closed type internals. The open type will be it is also further classified as blowing type and suction type. So here there's a image for this suction type internal. So the air is sucked from the atmosphere, and it leaves, and sucked from the atmosphere, and it enters the test section and into the tunnel, and it leaves the tunnel to the leaves the tunnel through this exit. So the main parts of this open type subsonic wind tunnel is, we have a settling chamber, we have this settling chamber, we have a wire gas, or we can say it as a grill. The settling chamber, we can say it as a flow straighteners, because we need a uniform flow through in the test section. And this grill, it removes foreign particles to enter the test section, because it may affect the model which is kept in the test section. And after the test section, we have this diffuser section, and before the test section we have this contraction section, or we can say it as an effuser or nozzle section. So this nozzle section, what it will do means it will increase the flow velocity, so that we can get the required velocity in the test section. And after that, in the test section, there is a pitot static tube. So there is one question, like they are asking in a low speed subsonic wind tunnel, um, the air velocity of the air is measured by using answers are pitot tube fixed in the test section, pitot and static tube uh, fixed in the test section, then a pitot tube outside of the test section, pitot tube at the rear end of the diffuser. So do you think what answer is correct for this? Whether they are keeping a pitot tube or a pitot static tube in the test section? Any answers? So there is a question in your gate exam some years before. In a test section, which is whether they are we are fixing a pitot tube or pitot static tube. Pitot static tube. Any guess? Which one is correct? Whether we are keeping this pitot tube or pitot static tube? Anyone? Hello, students?
Yes.
Audible?
Yes, sir.
Can you able to understand my question?
Yes. But
So I am keeping a device to measure the velocity and all, velocity of air inside this test section. So whether I am which one of the equipment I am placing inside this test section?
pitot tube.
Pitot tube or pitot static tube?
Pitot tube, sir.
No. Do you know who found out this pitot tube, and what is the purpose of this pitot tube?
Sir, pitot static tube is used in wind tunnel,
The answer is
so
pitot
that
static tube. The
they
second one is
can
correct.
they can measure static temperature and total temperature both.
Not temperature, pressure.
Sorry, pressure.
Yes. The stagnation pressure and the static pressure is measured. The stagnation pressure is measured in the, so the pitot static tube, it has two holes. One is it will be like this, the pitot static tube. One hole in front of the air and another hole, or here they will have it has four holes like this, equally spaced, and these four holes they measure the same pressure of the static pressure. The flow will be like this over the pitot tube, and it measures the static pressure. Here it measures the stagnant pressure, that is P naught. P naught is measured here, and P is measured here, that is static pressure is measured here. And based upon this, we will find the velocity of air. See this pitot tube, it is found by pitot, and it is used to find the velocity of water in a dam. So in order to find that only, pitot found this pitot tube. After that only this pitot static tube is come into picture, and they use this pitot static tube to find the velocity of air in this section. So that's all about the pitot static tube. And one more thing is there. Here they will consider so the stagnation point and the static point, there it is kept at a distance of 4d. Sometimes it will be at a 5d, and next real time distance will be, it is at 16d, or sometimes they may consider as 8d and all. Okay, diameter, d is a diameter of the tube. So the static and stagnation points are kept at a distance of 4d. Okay, and in supersonic tunnels and all, it will maybe kept at a 4 or 5d, I think so, because for neglecting the shocks over this tubes, so that the flow will be affected by this static pressure tubes. Static pressure is affected by the flow over the that means the shock over the filter tube. In order to avoid that, they will keep this distance quite apart. So then here we have the diffuser section. So after the test section, the flow should be reduced, the velocity of the flow should be reduced. So we have a diffuser section at the rear end. And one more thing, uh, there will be two pitot-static tubes kept in the wind tunnel. One is one in the test section, and another one in at the back of the that means at the diffuser section. And here at the rear end, we have a fan with motor, and it is a suction type, so that air gets sucked into the test section, and it leaves the wind tunnel. And also we have a rack of racks here, and smoke will be passed into the test section by using this racks, smoke racks, so that the smoke will be passed here. That is for flow visualization purpose. So the main advantages of yes.
So could you please explain that what is that 4D and 16D that you were explaining in pitot tube?
So actually, this a sharp in this pita tip is it is also a sharp corner. It will be like this only. Okay, it will be like this. So here and this is a stagnation point. After that, flow will get it will move on to the top surface and also the bottom surface of the pita tube, and it will reaches here. Here it is static points. Here are the static points which is kept at some distance apart. That is a 4d length, or sometimes it may be 5d and all. So for subsonic flow it is no problem, but for supersonic flow it is a problem, because this a shock will be, that means oblique shock will be formed over the front of this region, and it should not affect the static pressure regions in here. This flow should not affect the behind the flow. There may be some vortices, there may be some vortices or some irregularities in behind the shock. So if there is an irregularity, it should not affect the static pressure port behind the behind that. So that's why they are keeping this point some distance apart, so that it can minimize this effects and all. Okay, that's why they are keeping this like this. That while designing that you can see in your college wind tunnels itself, just go and check the wind tunnel, how much length it is, and where the static port is there, or a static port opening is there from the stagnation point. You just check it out and check the distance and all. You can find the distance like this, 4d or 5d, something like that. Yes. Okay.
Sir, why this second pitot tube in diffuser?
What I couldn't understand.
Second pitot tube in diffuser.
Yes, it will mention the different stagnation points at both section, and the static pressure points at both ends. In some test section, sorry, some wind tunnels it will be like this. In some wind tunnels there will be one static tube only. It will measure the both pressure or that means the head values, we will say H1 and H2 values. For that purpose they are keeping this. In some wind tunnels, I have seen in one wind tunnel that in low speed wind tunnel only, where they kept two pitot tubes, one at the effuser section and then the one at the test section, and they will get the difference of this both pressure values, and they will find the velocity of air. And one more thing, in order to find the or in order to do the calibration test, first what we need to do is we need to check whether the pitot static tube is correctly working, and we should blow some air inside the tubes of the pitot, and we should check that, and also we should keep the pitot at different altitudes, that means different positions from ground to, that means at the wall to the center, and we need to check the velocity at the near the wall is same, and the velocity at near the um, at the mid position of the test section is same, that we need to check it at same velocities, we are getting the same velocity at both ends, that we need to check. That is for a calibration test. And also one more thing, in a while testing in a wind tunnel, we need to so there will be lot of friction effect or shear stress effects near the wall section. So this subsonic wind tunnel, so here there is a one of the disadvantage, the flow quality is sometimes it is somewhat poor because of the shear stress effects in the throughout the walls of the section. And but the main advantage over this tunnel is it is a low cost, and we can have this smoke visualization, and there will be if since it is a open type tunnel, there won't be any accommodation of smokes and all here. And have you heard about this cross flow effect, cross flow jets and all, cross flow, this flame stabilization and all? Have you heard about anyone heard about that, this term and all? Flame stabilization, different types of flames, carburizing flame, like that. So, have you, anyone please reply?
No, sir.
So anyone gone to your kitchen in recent days and all? Have you seen in your gas stove and all, there is two types of flame, one is a blue flame and one is a red flame?
Yes, sir. Yes.
So what is the difference between the blue flame and the red flame? Then I will say this cross flow jet and all.
Complete combustion.
Yes, complete combustion. So this complete combustion, we will that's a blue flame is the complete combustion. So this complete combustion and all we need for this that means in the engine and all we need this complete combustion, and for rocket and all also we need this complete combustion. In if we are having the complete combustion only, we will be having high efficiency. So in order to produce that, we need complete combustion. So in wind tunnels, they will test this flame stabilization also in wind tunnel. Not only this only the we are testing the aerodynamic properties in a wind tunnel, we can test this flame stabilization also in a wind tunnel by uh, generating a cross flow and also a straight flow, that means an normal flow that will be entering into the test section, and also we need to give a cross flow jet. And because of the cross flow jet, and while and a burner should be inserted inside the wind tunnel, and because of this cross flow jet we can get more stabilization, that is a flame stabilization, the more combustion, the flame also it is more stabilized, and we will get more blue flame because of this cross flow jets. There's a lot of research works are going on for this topic also, so no need of this for your gate exam and all, so we can leave that topic. So the main disadvantage is poor flow quality, high operation cost, and it is very noisy, that you all had experienced this noisy thing because of this subsonic open type internal. Then here we have the closed subsonic type internal. So in a closed type we have the flow is get rotated inside the or circulated inside the tunnels, and because of this only the main advantage is the flow angularity or flow uniformity is very good in closed type internals. But the main disadvantages of this thing is we need some experts to operate. The cost is very high, and the design is also very complex for this, and we have because of this veins only, the flow angularity and the flow uniformity is very good in the closed type subsonic wind tunnel. Other all things and all, the diffuser, test section, and the same for both the open type and the closed type wind tunnel. First, what we need to do is we need to circulate some amount of air inside the wind tunnel, and after that the flow get circulated, and it continues. So these are the advantages and disadvantages of closed type subsonic wind tunnel. So because of the vanes here, the flow quality is good in closed type wind tunnel, and the operation cost is low, and but the construction cost is very high because of adding some extra vanes and ducting here, and the running condition is very hot because since it is a closed type, the open type the running is that means equipment, it won't get hotter than this closed type wind tunnel. The open type this it won't get too much hot. Then that's all for closed type wind tunnels. And next thing is the high speed wind tunnels. So the high speed wind tunnels means that is differentiated because of the Mach number. So in the subsonic wind tunnels also it is differentiated based upon Mach number. So if Mach number is greater than 1 inside the test section, we will get supersonic flows, and if the Mach number is greater than 5, we will get hypersonic flows. So these types of supersonic and hypersonic flow represents the high speed wind tunnels. These two types of flows represents the high speed wind tunnels. So there are the different types of supersonic and subsonic wind tunnels are blow-down type, in-draft type, then high speed wind tunnels, that is hypersonic tunnels. We have this shock tunnels, then gun tunnels. But the only disadvantage of this type of tunnels is there is a very lesser, we have lesser running time for this blow-down type and all hypersonic tunnels. The running time is very less. It is in milliseconds only. So the shock will be formed in milliseconds only. It cannot be, you can't hold the shock too much time. That is the main disadvantage of this type of tunnels. So I will explain how these types of tunnels are working for us. So here for a blow-down tunnel, we have a high pressure air storage. So this is also one of the biggest disadvantage of supersonic tunnels, because we need a large space or a large tank to store the high pressure air, or a large reservoir to store this high pressure air, and we should maintain that that air at a high pressure. And we have a pressure regulator here, and another one things. So in some tunnels, what they will have, we have a dryer, filter, screener for and a preheater for heating the gases and sending it into the this storage tank or into the reservoir. After that there is a regulator here. This high pressure air will pass into the test section or into the tunnel through this regulator, or by opening this regulator. And here we have this low pressure air chamber, so that air from the reservoir is passed to the low pressure air chamber here. So we know this pressure, temperature, everything, this flow parameters, it will pass from high level to low level. So this high pressure air is passed to this low pressure air chamber. So here the next parts of this tunnel is, we are having a settling chamber, we are having a nozzle. You know this already I have explained this type. That is we will be having two throats. One is the first throat and second throat. The first throat is for a nozzle, and the second throat is for a diffuser. So from the high pressure gas ejecting from this point is different, that we didn't mention earlier, but other things and all, we know that this high pressure air, it passed to the settling chamber, and it enters into the nozzle. So the speed of the air get increased when it leaves the nozzle. So this part we studied earlier about this CD nozzle. So the same thing is happening here because of the pressure ratios. We can easily visualize this. Here we are having the some pressure ratios at the exit of the nozzle. We are having some lesser pressure ratios. So because of this lesser pressure ratios, pressure, the high pressure air from the reservoir, it will be passed into the test section with high velocity. If the pressure is low, the velocity will be high. So we explained earlier, the mass flow rate remains same, but the velocity get increased and it will become supersonic. So because of the under expanded conditions and all, we will be having supersonic flows here, and we will be testing the model by fitting the model in the test section, and the model get tested. And after that, we know the flow should not be supersonic when it leaves the diffuser, so that we have a diffuser section at the rear end of the test section. The diffuser section, what it will do means, it will slow down the speed of the air. The velocity of the air get reduced in because of the diffuser, and it reaches the air chamber and it gets stored. When the pressure get equalized, that the pressure at the air storage and the pressure at the low pressure air chamber, when it get equalized, the flow is stopped. And that's all for this blow down type wind tunnel. And the main disadvantages, these things and all, just for your understanding purpose, it is enough, because there's no questions for specifically for this flow down tunnels, and they won't ask such type of questions, but they will ask questions from this throat sections. Why there is a large throat at the diffuser? What is how we can find the area of the larger throat by giving the value for this first throat area ratio for this first throat, or else the area ratio for this both throats, that is 82 divided by 81, that they will ask. That is 82 divided by 81 equal to P02. That one formula we have seen in our last class. Just remember that formula. That they will ask from this type of sections. And so the advantages are, here we have a high Mach capability, low construction and operation costs, superior design for propulsion and smoke visualization, and since smaller loads on model during startup because of faster starts. And main disadvantage is shorter test times, that is running time is very less, need for pressure regulator valves, and it is a noisy operation. These are the disadvantages. The next thing is the continuous wind tunnel, or it is a closed wind tunnel. The closed wind tunnel is both for subsonic and supersonic. We have closed wind tunnels, but in supersonic we have the main difference is we have this both two throats for increasing the velocity and decreasing the velocity. We need this two throats and all. That's the only difference here. Then the next thing is the shock tunnels. So we have this hypersonic tunnels as a shock tunnel, and there are two types of tunnels. Other tunnels also there: plasma tunnel, hot shot tunnels, shock tubes. That also hypersonic tunnels only. But no need of all those things here. We can see there's one or two tunnels here. Now we are going to see this two type of tunnels only. One is the shock tunnel and another one is gun tunnel. The main difference for shock and gun tunnel we will see here. So shock and gun tunnels. In shock tunnels, shock will be formed because of the pressure difference or the between the gases inside the tunnels, or inside the two sections, or inside the shock tubes. Here we have the driver section and driven section, and both are separated by two diaphragms. So one of the main application for this shock tunnels that I will say now. Now they are using shock tunnels for packaging So it is used for packaging itself. They are using this shock tunnels, and also some purpose like in farms also they can use the shock tunnels to what to say. Uh, that means some crows or some birds, if they are or some elephants, if they are entering, means by using this we can get rid of that animals from our farms. For that purpose also they are using. So shock tunnels are nowadays used for wide applications, or some commercial applications also they are using shock tunnels. And in Bangalore, one person is they have made this shock tunnels, and they are distributing tunnels for this type of purpose also. Okay. Okay, fine. So this shock tunnels, we have a high pressure region here, high pressure gases here, and we have low pressure gases here. And both are separated by this diaphragm. And when this diaphragm, when the pressure increases, this diaphragm ruptures, and high pressure gases, it flows into the low pressure section, that is the driver section. It from the driver section to driven section, and it reaches the second diaphragm. This second diaphragm, it get ruptures because of the high velocity of air. And this because of the rupture of the second diaphragm, the flow will be supersonic, because here the pressure will be way less when compared to the driven section. When because of the rupture of the first driven section, the hot gases will eject through this second diaphragm, and it reaches the test section by using this nozzle, and the speed get further increased because of this type of nozzle, CD nozzle here. And supersonic flow, or sorry, hypersonic flow is achieved here, because in order to increase the flow from supersonic to hypersonic only, we are having this nozzle, and the flow is increased to hypersonic level. And then it reaches the dummy tank, and the uh, flow will be stopped when the pressure will be equal from here to here. Now from in both sections, when the pressure get equalized, the flow gets stopped. The flow duration for this shock tunnel is, it is 1 millisecond. The next one is the gun tunnel. So in gun tunnel, the main difference for shock tunnel and gun tunnel is, here we have this two this pistons. Sorry, here we the piston is moved free by using in this by firing the piston, firing the rear end of the gunpowder. By firing the gunpowder, the piston is moved at a high velocity, and it hits the hit this wall, and this wall get ruptured, and high, high velocity gases get ejected into this nozzle. And because of this hypersonic flow achieved in this test section, and the model get tested here. And this type of this is the main process here. So we can see the diagram before firing and after firing in this session. So here before firing, the piston is at the rear end, and after firing it hits the walls of the this wall, and it moves here. And the diaphragm here, it will because of the sound, the diaphragm get ruptured, and hot gases get ejected here. It enters the test section. Here this is the tunnel section. Here we are having the nozzle here, and hot gases, it enters the tunnel, and the model is getting tested to the here, and it reaches the vacuum tank. This is the process for gun tunnel. So other I will write the other type of tunnels also, like plasma tunnel. Just remember the name, they won't ask, but just remember the hot shot tunnel. Hot shot tunnel. Hot shot tunnel, and also shock tube, shock tube. So one more thing, the Prandtl Ludwig, he designed one tunnel. The tunnel is called closed type tunnel. So the closed type tunnel is also called as Prandtl Ludwig tunnel. Okay, just remember this. Prandtl designed a wind tunnel. That wind tunnel is a closed type wind tunnel, and closed type. So the closed type wind tunnel is also called Ludwig wind tunnel or Prandtl wind tunnel. Okay. Interrupt. So these are the other types of tunnels available. Also, in olden days, some other tunnels are also there, but no need of that and all here. So next thing is the wind tunnel balance. So do you know why we are using this balance here in a wind tunnel? Balancing setup for a wind tunnel. Do you know why, guys? You guys know why we are using this wind tunnel balance in a wind tunnel, balancing unit in a wind tunnel? Anyone?
So for measuring loads,
Yes, sorry. Which type of loads? What is a 3 component balance and a 6 component balance? What is the difference between that? Have you ever heard this or come across this word, the 3 component balance, 6 component balance?
I didn't
No,
remember,
sir.
sir.
Okay. Uh, have you heard this word like lift, drag, side force, um, yawing moment, pitching moments, and all?
Okay.
Yes. So if 3 component balance means it will measure only side force, then lift and drag. If 6 component balance it will measure remaining things that are rolling, yawing, and all. It will pitching moment, everything it will measure. So a balancing unit is a device which is used to measure the forces inside the wind tunnel. Forces are inside the wind tunnel models. Okay, in the wind tunnel models. So different types of balances are pyramid type balance, wire type balance, strut type balance, yoke type balance, platform type balance. So these are the different. Pyramid type balance will be like this. It is like this. Over the top, the model will be placed like this. So the balancing unit here we can see like that. This is the type of balancing unit. Here the unit will be, sensors will be placed here. So if airflow is over this model, the model gets, if the model is getting it is there is a drag in the model, it will move somewhat this rod, it will move some backward, so that drag force will be created, and it is measured by using the sensors here. It is fitted here, and a lift force is created, that is also measured by the sensor inside this, and it will be shown in the data acquisition unit outside of the tunnel. Same way the yaw forces and all. So if we are having only lift, drag, and any one that means side force means that is called 3 component balance. If we having we can measure the remaining things like a moment, rolling, yawing, and all means, then it is called 6 component balance. So these are the 6 type of balancing systems used in wind tunnels. Or one more thing is there, strain gauge balance. Sorry, and I didn't mention it here. There is a strain gauge balance. Okay, strain gauge balance. Then next thing is the flow visualization techniques. So there are different types of flow visualization techniques. That is a smoke technique. That is the this thing, and the second thing is the commonly used technique in most of the colleges, most of the internals in most of the colleges. Okay, so smoke, we are using smoke by using some wood smoke or some kerosene smoke. We uses kerosene to form this or to generate this smoke, and we will pass this smoke to through this racks like this. You may saw this type of systems in your internals. Like this it will be. These are the racks, and smoke will be passed uniformly all over this rack, and it will come out of this racks, and it will flow over the surface of the aerofoils over and under the aerofoils, and the flow will be visualized. And also we can visualize dyes are also used for visualizing the flow, but that was in water channels. The stuffed type, if this is a model, we will be having small thread like tufts over fitted or pasted over this surface of the wing model, and by when the flow is over the aerofoil, this tuft will say the flow where there is any the flow over the aerofoil, is there any turbulence, we can see from here. And third one is interferometer, that is a Mach center interferometer technique. And fourth one is this, by using the density variations we can visualize the flow over the aerofoils or some models. Then the clearance technique and the shadow graph technique. Here we will be having the density gradients as a square of density. Here we will be having only the density gradient. Here we will measure directly the density of air, variation of densities. And also this type of techniques are used to visualize the shock over the wing, and it will be formed in a projected in a photographic plate, and we can visualize that. These are the flow techniques. And other techniques are also there. Oil flow type, that is by using some oils, and we can visualize the flow. And also some other types are also there. Helicia apparatus is also used to visualize the flow over some models. The apparatus will be like this, and some flow straightness will be at the top of the Helicia apparatus, and the flow straightness will be at the top of the flow apparatus. And but the main thing is we can't visualize in any air flow of air over the models, but we can visualize the flow of water over the model. The water is flowed over the model, and we will allow a dye to flow over it, and because of the dye, the flow over the model is get visualized easily by using this Helicia apparatus. Then the flow angularity and flow directions are measured by using this yaw spears and claw yaw meter. Spear and yaw meter. Yaw spears and yaw meter. The yaw spears and yaw meter will be like this. It is kept inside the tunnel, and it will have two ports like this, and then two ports will be kept at some angle, and each port will measure the same pressure. And by using this they will measure the flow angularity, at which angle it is flowing. And suppose the flow is at some angle of psi, means then the yaw angle will be psi, and they can measure by using this device, these two types of device. So yaw spear and claw yaw meter is used to measure the flow direction of inside the wind tunnel. Okay, fine. So that's all. But we have two things that we will say, you can see later. Now we can solve the sum. So here we have a problem. Consider an ideal flow of density rho. So the density will be rho through a variable area duct. So the area is variable, consider like this. So the area will be as shown in the figure, so that I can draw the image here. This is 1, region 1 and region 2. Let the cross sectional area of the section 1 will be, so that here the area is A1, here the area is A2, here it is A1, here it is A2. The velocity measured at the section 1 using a pitot static probe is V1. So the velocity measured at section 1, here the velocity is V1. Then the static pressure drop is P2 minus P1. P2 minus P1 is, so here we have the sessions like A1 and A2. What we need to do is we need to find the velocity, static pressure drop across this variable duct. So do you have any idea for finding this static pressure drop across this variable area duct? Guys, can you able to hear me? Do you guys have any idea for finding this variable pressure drop across this variable area duct?
Sir, is total pressure remains constant?
No. They itself say there is a static pressure drop here. No need to consider the total pressure and all here. Just consider the static pressure drop only. No need to consider the total pressure over the session. This is a simple question only. Don't go beyond that. Huh? Okay. So they have given another one term, the consider an ideal flow of density rho. So the rho remains same. Okay. So shall I solve this sum, or you guys can do that? Okay, fine. I will tell how. So this is a variable area duct, and they doesn't give any values for this area, velocity and all. So only thing is they ask us to find some expression for this pressure drop. Okay. So in order to derive this expression, first we know m equal to, this m equal to rho a v. Okay. So from that, rho into a1 v1 equal to rho into a2 v2. From that, rho get cancelled, and a1 v1 equal to a2 v2. So from that, v2 equal to a1 v1 divided by a2. These things we know, and also we know this equation, like p1 plus rho v1 square by 2 equal to p2 plus rho v2 square divided by 2. So what they asked us to find the pressure drop. So that by interchanging these terms here and all, we know this p2 minus p1 equal to rho into v1 square minus v2 square divided by 2. So this answer is also correct only, but we can make the expression in terms of area ratio, because they have given the area also. That's why I'm doing another one simplification here. That is rho by 2 equal to so here we can say like this v1 v1 square minus, so for v2 square we can write like this a1 by a2, so a1 by a2 into v1 square. This is also this whole square. So this alone we can write like this rho by 2 v1 square into 1 minus a1 divided by a2, sorry here whole square. Okay, so the pressure drop equation is P2 minus P1 equal to rho by 2 into V1 square into 1 minus A1 by A2 the whole square. This is the answer for the pressure drop across the section for this variable area section. Actually this is the formula, just note down this formula. This formula you should remember this formula for solving some sums regarding wind tunnels and all, because they will be asking this type of sums only for wind tunnels and all. Okay, just note down these things. Remind me when you finish. Okay.
Yes, sir. Done, sir.
Yes, you have done. Okay, thank you. Then we have another one formula also. Suppose if we need to find the value for V2 square means, so V1 square formula we need to find. If we want to find the V1 from this, we can find the V1 formula, correct? V1 value. Okay. By using this relation, we can easily find the V1 value. But in order to find the V2 value, same the formula will be 2 into square root of 2 into P1 minus P2 divided by rho into A1 divided by A2 the whole square minus 1. Just note this formula. Same way for V1 also write this equations like this. From this relation, write the equation for V1 also.
Sir, it's A2 by A1 in V2. It's A2 by A1.
A2 by A1, I think so. Okay. Have you solved that?
Yes, sir.
Okay. A2 by A1. Okay, fine. A2 by A1 the whole square minus 1. Just write the equations for this V2 and also for formula for that's A1 V1. So sometimes they will give the value for area ratios and they ask, and then the pressure heads, and they ask us to find the value for velocity at the inlet section, or sometimes they ask us to find the velocity for the exit section. So if they, that means in the contraction exit in entry of the contraction zone and the exit of the contraction zone, they ask us to find the velocities. If both things they are asked means, you can use these relations to find the answers. Okay, they will give the pressure at both section, and they will give some initial value or final value at one section, and they ask us to find the remaining thing, so that by using these things we can easily find that. So so this sum we have already solved yesterday by using this simple formula only, but we have another one formula also. Just no need to solve this sum, but just note down the formula. That is V2 equal to square root of 2 into W del H divided by, that is P1 minus P2 equation, that is equal to 2W sorry P1 minus P2 equal to W into del H. That's the thing here. Okay, other all things same. The formula is 1 minus A2 divided by A2 divided by A1 the whole square. Okay. We know from this W equal to, that is a specific weight, specific weight. That means density into, that is rho into G. Specific weight equal to rho into G. So that rho is 1000 and G is 9.81. From that you can get the answer for W. And one more thing, del H value. Del H equal to point, that is 40 centimeter. You can write like meter. In meters we can write like this: 0.4 meter of water column. No need to convert anything here. Just substitute the value, and by using this specific weight and this del H, substitute the value here and find the value for the P. Okay, same problem only. Just only thing we change here is W into del H. For that P1 minus P2 divided by rho, we are substituting as W into del H. That's the only thing we are substituting here. Just substitute the values and easily find the answer, or else you can use that also, that formula also, or else just use this. Okay, then here are two things I need to show here. First is the CD nozzle. In the last class itself we have seen this CD nozzle. This is the perfect graph for that flow or the CD nozzles and all. So you can see here from A to C, you can see here from A to C the flow is subsonic flow at the nozzle exits. But then from C to E, subsonic flow only, but at nozzle exit, but shocks inside the nozzle. That means because of the shock, the flow becomes subsonic after the shock. That means here we can see the sonic condition here. I told that before sonic condition, the mass flow rate is changing, but after sonic condition, there is no change in mass flow rate. The mass flow rate remains same, and here the pressure here is they won't communicate with the pressure at the rear end, so that's why there is no change in the mass flow rate and all. And after that only, the here you can see a increase in pressure because of the shock or normal shock formed in between the nozzle duct. That means at the divergence section here the normal shock will be formed. After that, this shock, it moves till the rear end and it will form here, and then the conditions like under expanded conditions and all, it will exit. That this the exit pressure is less than the PB, means the flow it will move outside, otherwise it will get stopped here, or the nozzle here the normal shock will be formed at the exit of the nozzle, and if P equal to PB, it will be formed here. After if it is go beyond or the value is getting lesser beyond the exit value, that means a PB value, the shock will be formed out, it will move outside, and Mach number greater than supersonic speed will be achieved there, otherwise it will become subsonic only. So this is the main thing for CD nozzle. In the last class we have seen this up to the sections or the graph up to here only. The remaining sections and all I have explained in the next graphs, but here all are combined, and you can easily identify from this type of graphs and all. This from this graph. Okay, this is about the CD nozzles that we have discussed in last class. And here we have the theta beta m curve for Prandtl-Meyer expansion and all, and for also for this shock, oblique shocks and all. We know the for a specific these are this curve represents the Mach number values. So for a specific theta and beta value, the Mach number will be, we have a specific beta Mach number that is shown here, The exact curve is in gas tables. If you have gas tables means you can have the in the rear end. That means at the last page of the gas tables, they will provide a big graph. That graph is based upon this theta beta m curve only. That is the theta beta m curve. In that you can easily visualize this weak and strong shock. And the strong shock you can see here the theta equal to theta max. In the here it is a weak shock. That means oblique shocks are formed here, and here it is a strong shocks are formed, and the Mach number is less than 1 after the strong shocks. Here it is greater than 1 only. So for a particular theta value and a particular beta value, you can easily identify the Mach number. Or if they are giving the value for both Mach number and theta value, you can easily find using this Mach number and theta value. You can easily find the beta values. That is the shock wave angle. Okay, if they have given the beta value and Mach number also, we can also find the theta value also. That is a deflection value also, deflection angle also. You understand this thing? You just understand? I hope so. So in your question, suppose they are giving a curve like this, and they are mentioning the this is Mach number m equal to 2. So this is a Mach number m equal to 2, and they ask us to find this point. At this point it is m equal to 2 means they are asking to find that means here it is 42 degree or 47 degree. They are given the value for 42 degree, and they have given the value for Mach equal to 2 in given data. They ask us to find the beta value means for corresponding theta value and corresponding curves, just draw like this or keep a scale or something to denote the beta value, and mention the beta value or find the beta value like this. Okay, or else if they have given the value for beta and theta means just draw like this or keep like this and find which Mach number it is, which line and the flow of extreme the downstream Mach number is which Mach number. Just find it from this curve. If they are giving curve in GATE exam, suppose they are not giving curve and values other things means, or gas tables or some values from gas tables means you should use your formulas to find the downstream Mach number. Okay, if they are giving this curve means use this curve to find the answer for the downstream Mach number or some theta or beta value. Or if they are not giving the curve and are not mentioning the gas table values means only use your formulas to derive the answers or come up with the answers. Okay, so this thing. So that's all for our from aerodynamics class. And so now I will tell you from which part and all maximum questions will be focused. Okay, so the first part means some there will be questions from source sink pair, that is rank in oval, then half body index, half body oval, rank in oval, then vortex flow, circulation. So just focus that parts because you there will be some questions regarding that source sink. They will ask questions like this: if a source and sink is combined, what will be happening? If source, sink and uniform flow is combined, what will be happening? What is a doublet? What is a combination of doublets? Like that some questions will be. It may not be a problematic question, but it may be a objective type, like simple objective type only, but it will be a confusing type question only from that part. The next thing from Kutta condition, they will ask us to find the lift values or some from circulations and Kutta conditions. There may be some questions, and definitely there will be questions from thin airfoil theory and also from normal and oblique shocks. Maybe somehow there will be questions from thin airfoil theory and also from normal and oblique shocks. Sometimes if the questions, I think in this time they are taking questions from IIT Bombay. Uh, so somehow it will be tough only. The questions will be tough only. So I think so. They will ask questions from this Prandtl-Meyer expansion, then also from thin aerofoil theory, and also from see this elliptical lift distribution also. There are some minor difficulties, not difficulties. They will ask, give the value for gamma, some values, and they ask us to find the value for lift. So substitute the value of the formula for lift, some 4 pi, like formula we studied in some previous classes and all. Use that formulas and substitute the value for gamma there, and find the answer for the lift.
Recording has stopped.
Excuse me, students.
Yes, sir.
Yeah.
Yes, it is audible for you.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. So these things just focus. Then in wind tunnel portions and all, just 1 or 2 equations only. Okay. Sometimes this contraction ratios, sometimes questions will be for in wind tunnels and all other things and all. They won't focus, give some other too much importance in these type of topics. Just to focus on this shocks, and also thin aerofoil theory, lift distribution and all. Then in the initial topics, that is from Naka series, study the Naka series thoroughly. That means Naka 4412, we have the different series now. Just study the Naka series thoroughly, because the questions may be from there. Then what is the use of leading its slats, then flaps, why they are using flaps. They won't ask like why they are using flaps. They will ask questions regarding that, whether it is a high lifting devices and all. In high lifting devices and Naka series, uh, definitely one questions will be there from Naka series. Maybe they will ask like what is the design value of lift in some this year of while, what is the value. They will ask like that. Find the value for the design cl design lift coefficient, and also the symmetrical and symmetrical aerofoil that decide the camber location of this, that and all. Just focus in a thin aerofoil theory, that is a moment coefficient. That means they won't ask like a moment coefficient, they will ask a pitching moment coefficient about leading edge or about trailing edge. They will ask questions like that. Okay. And also first I told that in Rangin oval, in Rangin oval itself, on small confusion and on a problem is there. Just take that what I will tell you. In JD Anderson, I will show you the. So in order to find the distance of the first and second stagnation point, I think they have covered the topics regarding this. Just note that formula. They ask us to find the value for the stagnation points. That is an important question. If in IIT Bombay and all, the questions will be tough. Means they will definitely ask from that part and all, because the questions will be like that only. Okay. They ask us to find the stagnation points from the for half body index, and also for this Rangin oval and all. The stagnation point before the source flow, and also after the sink flow, there will be 2 stagnation point, one before and one after. And we have a specific formula for the location, particular location. Note that formula and just remember that formula also. Okay. So that's
Sir,
all.
it's given in JD Anderson, no?
Yes, it is given in JD Anderson. Just note that formula. Yeah, and these things and all, just remember and study the formulas thoroughly. and things I told to note down this point, note down that parts means that things you just remember, because from that part only uh, importance will be given. That's why I have told like that this part it is very important, this part it is very important and all. Okay,
Okay, sir.
okay,
Sir,
okay.
I am having some doubts, sir.
Yes.
Sir, what about moving shock, sir? Numericals from moving shock.
What?
Sir, moving shock.
Moving shock. So moving shock and all, it is an unsteady problem. They won't ask from moving shocks and all, because in our syllabus and all, it is not focused about moving shocks and all. It is about some unsteady problems. We can't picturize the values for or properties behind that moving shocks and all in this. Okay, so no need of that and all here. That
Okay.
okay, that depends upon some unsteadiness in the flows only. That's why it will happen about moving shocks and all. No need of that here. Just focus
No.
on that static shocks and static properties only. Okay.
Okay. Sir, is there any condition for oblique shock to form in CD nozzle, inside the CD nozzle?
Yes, it will form the as I told no. First normal shock will be formed. After that, the because of if there is a object like a model inside that inside not in inside that, after the nozzle only it will become uh, oblique. Okay, in the CD nozzle it will become um, like it
Sir,
will
it
become
becomes
parallel
oblique at the exit when the flow is under expanded.
extended.
But is there
After
any condition to where that oblique shock will form in inside the nozzle,
no,
just like normal shock?
no, it won't form like that.
Okay.
Yes,
Or sir, what will happen if the normal shock forms at the throat of CD nozzle? Uh,
normal shock is formed at the throat.
yes,
It
sir.
is there won't be any flow after that. It will get choked. That is the only condition. It is formed there only at the throat only. After that, it will move somewhat downstream.
अच्छा 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 अरे हाँ 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 yes sir.
Okay.
Sir, sir, एक one more thing, sir. So what about if they ask about the find the location of normal shock? मतलब they have given exit throat area, sorry exit area and the throat area, and they are asking about find the location of normal shock.
Uh,
So these type of questions was there in the syllabus.
yes, I have also come through one, this type of question before. So I will tell you in if there is any possibility that I will sometimes I will take classes for you in flight dynamics and all. If I am taking means I will explain you at that time. Okay, or I will somehow I will come up with answers for this. Huh? So if
Okay, sir.
you guys have any doubt means you I think you guys note down my number. You just message me. So if I have time means I will definitely tell you how, or I will solve the doubt for you guys. Okay.
Okay, sir. And sir, I will remind you in the next class of flight mechanics.
Okay, fine. Because
And sir,
they have one question. I also come across that question to find the distance of that. But now I didn't remember that thing. I will definitely I will help you with this. Okay.
yes, sir.
Uh, okay, fine. So
Sir,
if you guys
notes.
have any, yes, notes will be uploaded. I will send the notes to your team, wings of our team, so that they will upload the notes. Okay. Previous notes also I have sent that notes.
Sir, that
Other
notes of elliptical lift distribution also, sir.
yes, sir, that already I have sent that elliptical lift distribution and all.
No, sir, they are
Previous
not uploaded.
previous notes only I haven't sent it. The last class and this class only I haven't sent notes. That also I will send. If any notes you want means I will send it in personal also, or else I will give everything to wings of our team. You can just collect it from them. Okay.
Okay, sir. Thank you, sir.
Okay.
Sir,
Yes.
for hello, sir.
Yes.
Sir, for multiple selection questions, which topics we have to focus more, sir?
Yes. Just focus on That's why I told. See, lift distribution, thin aerofoil theory. Then this normal shock, oblique shock. Then finally, um, then questions from isentropics also, isentropic relations, that is from what is changes of static temperature, static pressure, total stagnation points. That is from normal and oblique shocks. Just remember that. Then from circulation, vortex, these things and all important. Then the source sink where these things, it's important. Okay. This for Prandtl-Meyer expansion. Uh, Sometimes there is a questions in I have come across some questions in gate questions before. Most questions they have asked some from oblique shocks and Prandtl-Meyer. That oblique shock they are morely focusing on oblique shocks. Normal shocks you can easily answer the normal shock questions, but in oblique shocks some difficulties are there. The beta angles and all, whether it is increasing or decreasing, or the theta beta m curve, shock, not shock polar, the sonic circle and all, whether it is in an oblique shock or in a detached bow shock, where the normal shock is, where the weak shock is, where the strong shock is, that and all. Some questions are there. Okay, just
Okay, sir.
focus on oblique shock, normal shock, Prandtl-Meyer expansion. Just note down the formulas, note down the important points you have gathered from here, and also that's enough. Then this Fano flow, Rayleigh flow and all, just note down that Mach number, whether it's increasing or decreasing. That part is enough. No need of too much complications, and you will forget everything. So just remember those things. Okay. So see, in aerodynamics, propulsion, these things in aerodynamics and propulsion only most questions are there. So just focus on aerodynamics, then propulsion, and you can
Oh,
easily get some marks. Okay.
okay, sir.
Okay. Fine. This time, so we can wind up the session. So if you guys have any doubt, means you can message me, or you can ask your wings of your team, so that I will help you out for your doubts and all. I will clear your doubts. Okay. Thank you once again. Have a happy Diwali ahead.
Thank
Thank
you,
you.
sir. Happy Diwali, sir.
Bye.